will have the maximum what? Maximum compression, right? So the question asks for maximum stress. Okay, down here you have tensile compression. When we were dealing with brass, right? We will get only maximum tension, right? If we look at point A and point B, they are both maximum tension. There is no what? So I put a positive down here. There's no compression. And why is that? This is because of the moment about Z. They're in the tensile side, and moment about Z is very high relative to moment about Y. Okay, so there's no compression. Whereas for the steel, right, you can have maximum tension, okay, which is point I, and we have maximum compression, which is point K. Okay, so now we are we clear? This the thing about this course, okay, putting the numbers is straightforward. Okay, it's easy. Is you have to know identify which point to calculate. Okay, so that is why this course is deemed one of the toughest courses in mechanical engineering. Okay, for this simple fact. The other one is heat transfer. It's also really tough. Okay, so from here, because of the analysis part, we are going to calculate stress X at point I, right? So Px, so we calculate the steel is 1.359 times 10 to the power 6. Right? And then we have plus, then we will have 200 divided by 104. And then we have to have our My. My is 375. So we are calculating point I. Point Y, everything is in tension. Okay. And then the Z distance of point Y. Okay, the Z distance of point I. Okay, so this is Z. Again, a lot of times students get this wrong. Okay, so it's 0.01 divided by 2. Okay, you have to be really, really careful over here. Then you divide by IYY. So IYY we calculate to be 2.859. So 2.859 times 10 to the power minus 6. Then plus again, because we are dealing with steel. And then we have to consider our moment, 17.936. And then multiply by distance. So we know that this is a small y. This y distance is what we need to know. So the centroid, let me move this across. So we just need to minus 10 millimeters. So the centroid is, can't remember now, 123.207. So 123.207 times 10 to the power minus 3 minus by 10 times 10 to the power minus 3. Why 10? Because this distance from here to here, this is 10. Okay. Then divide by the I, which is 65.694. Times 10 to the power minus 6. Okay. So this is equal to 1.359 times 10 to the power 6 plus 200 divided by 104 times 375 times by 0.01 divided by 2 divided by 2.859 power minus 6. 1.261. Then plus 17.936 power 3 times by bracket 123.207 power minus 3 minus 10 power minus 3 close bracket divided by 65.694 power minus 6. 59.438 or 59.439. So 1.359 power 6 plus 1.261 power 6 plus 59.439 power 6 is equal to 62.059 positive. Okay, so that is our point I. And the next thing we are going to calculate so this is our maximum tensile. Okay, then we're going to find our maximum compression, which is stress X at point K. Okay, so the axial load is still tensile. Now what changes is the next two things are negative, right? So minus 200 over 104 multiplied by 375. Now the Z distance for point K is still the same. So 0.01 divided by A, no 0. So 0.01 divided by 2, and then divide by 2.859 times 10 to the power minus 6. It's still the same because the Z distance is still the same for both. Now this is the part that changes. So minus by 200 over 104. Moment is still the same. And then divide by the second moment of area is still the same, 65.694 times 10 to the power 6. This part is different, so now it is equal to 0.3 minus by 123.207 times 10 to the power minus 3. Right? Why is that? Because we know that this is our 123.207, and then the overall height is 300, right? So this distance from here is 300 minus 123.207. So 300 minus by 123.207. Okay, that's why. So from here, the first value is still the same. Now the second value now is minus 261 times 10 to the power 6, and then you just need to calculate the third value. So 200 times by 200 times by 17.936 power 3 divided by 104 divided by 65.694 power minus 6 times by 0.3 minus 0.123.207 power minus 3. Close bracket, syntax error. 5 times 123.207 times by 17.936 power 3 times by 200 by 104 by 65.694 power minus 6. 92.824. Okay, I get 92.824 times 10 to the power 6. 1.359 power 6 minus 1.261 power 6 minus 92.824 power 6 is equal to minus 92.726. Okay. So that is our maximum compression. Now note that only in the steel section that stress X goes from tensile to what? Compression, right? So if we look at this thing again, so we know that at this point over here, at point I, right? Our stress X at point I is equal to 62.059. Then at point K, right, we have minus 92.726 times 10 to the power 6 Pascal, right? So what we see, so we call this our point I, J, K, and L, right? So what we realize now is the neutral axis will fall in the steel section only, right? Because for the brass, right, material one, everything is in tensile. Okay, everything is in tensile. There's no compression. Okay, everything is tensile. There's no compression, right? Whereas for the steel, right, point I is already in tensile mode, and then point K is in compression. Okay, so we now know the location. We now need to locate. Okay, we now need to locate the position of the neutral axis. Okay, we now need to. So if we look at the true form, okay, the true form of the equation, the true form. True form means the positive in which direction. Okay, that's where we have to be careful. So now this is the true form. So if we were to have our transformation, I'll use different color. Okay, so this is our y, and this is our z. Okay, so the true form of the general equation looks like this. Okay, so it has stress x is equal to, now the axial load is always 1.359. Okay, so this is 1.359 times 10 to the power 6. Okay, and then we have minus, then we have the formula n, or this will be positive my over iyy multiplied by z minus by n mz over izz multiplied by y. Yz is negative because positive by right should be pointing towards the right. This time the z is pointing towards the left. That's why it's negative. Now, based on the true form, okay, based on the true form, right? If you use right hand rule, this is my positive, right? If you use this equation over here, the true form equation over here, my positive is in this direction. Okay, right? But for our case, right, things goes opposite. Okay, why I say things go opposite? If we look at our moment about y, our moment about y is in the opposite direction relative to the blue. Yes or no? Can you see that? And then our z is also our this is mz. Our mz is also in the what? Opposite direction. So when it's the opposite direction relative to the true form, okay, we just need to put a negative. Okay, so based on the true form now, this is important while locating the position of the neutral axis. Okay, so write this down first. Okay, based on the true form, right, we know that my will be now minus 375, and then mz will be equal to minus 117.936 times 10 to the power 3 Newton meter. Okay, because in the true form equation, which is the one I'm putting in a blue box, right, is derived based on the transformation where y is going up, z is going towards the left, and we are gripping using the right hand rule. Okay, so now the first thing we want to do now is we want to locate. Okay, we would like to locate where the neutral axis intersect J or intersect J K line. So JK line